So let's talk about goodness of fit. Now, a goodness of fit test is used to test the hypothesis that an observed frequency distribution fits some claimed distribution. So for instance, we take a look at number 20 here. In number 20, we have the categories here are race or ethnicity. So we have one, two, three, four, five races or five categories, five different classes. And the distribution here, the middle row is the distribution in the general population. So these are the percentages or the proportions of each of these individual racial or ethnic groups in the general population. And on the bottom, we have the number of each one of these races or ethnicities, or the number of each one of these that are represented in 4,297 clinical trials. So that would be 4,297 clinical trials. So in these 4,000 trials, or 4,297, 3,855 of the people in those clinical trials were white, non-Hispanic. 60 of those people of this 4,297 were Hispanic, and so forth. So therefore, here we have the observed distribution. So what we're going to do is we're going to have a test to see if our observed distribution matches up with our expected distribution. And the expectation would be that this distribution, the observed distribution, would match the general population. All right, so if there were no bias in the clinical trial, that is, if there were no bias in the clinical trial, then you would expect the sample to match pretty closely to the general population. So that's what we're going to be doing. We're going to be conducting goodness of fit tests, which are used to test the hypothesis that some observed frequency distribution fits some claimed distribution. All right, so let's take a look at some of the notation we're going to have to use. And well, O is going to represent each observed frequency. So we're going to have a list of frequencies that we saw, like we saw in that last example. And those are going to be the observed frequencies. We're going to label each one of those frequencies O. And then E is going to be our expected frequencies. So we're going to have O's and E's, observed frequencies and expected frequencies, and we're going to have K of those, because K is going to be the number of classes in our frequency distribution, the number of categories. And N is the number of trials, and N is just the sum of all the frequencies. So the sum of all the frequencies is equal to N, and K is the number of different frequencies, or the number of classes in our frequency distribution. All right, we're going to be using a chi-squared test statistic. So the test statistic is going to be chi-squared, and it's always going to be a right-tail test. And we're going to use K, which is the number of classes or categories, minus 1. So K minus 1 is going to be the number of degrees of freedom. So degrees of freedom are equal to K minus 1. And it's going to be a right-tail test. So, and it's actually, the chi-squared distribution is skewed to the right. So we're going to find a p-value using the TI calculator as the area to the right of the test statistic once we find that test statistic. Okay, so our expected frequencies, if we can assume that the frequencies are equal, then our expected frequencies are going to be n divided by k. We're going to take the total number of observations and divide it by the number of categories, or the number of classes. And if the expected frequencies they are not equal, then the expected frequency is going to be the number of classes times p, which is the probability for that individual class, or the proportion that should be in that individual class. Let's take a look at this example here, number 10. And for number 10, it's about occupational injuries. It says, randomly selected non-fatal occupational injuries and illnesses are categorized according to the day of the week that they first occurred. and the results are listed below. So we have here a frequency distribution with categorical data. The categorical data is going to be the month, or sorry, the day of the week in which uh, injury occurred. I guess this data could also be ordinal because there could be some order. Uh, but anyway, so the categories are the days of the week, and there are 5 days of the week, the work week actually. So we have 5 different categories. So K is going to equal 5. All right, and we also have N is the sum of all of these frequencies. So this is the frequency in which injury or illness occurs on each of these individual days. And if you add all these up, if you add up all the frequencies, we'll get N, which is equal to, in this case, 107. 107. All right, so now what we're going to do is we're going to look at doing a hypothesis test. So we want to use a zero point zero 0.05 significance level. So I have alpha. Alpha is equal to 0.05. And to test the claim that such injuries and illnesses occur with equal frequency on different days of the week. So we want equal frequency. All right, so since we can expect the frequencies are equal, E, or the expected frequency, is just going to equal N over K. And we have N and K right here. N is 107 and K is 5. So in this case, N over K is going to be 21.4. So E then, which is equal to N over K, is 21.4. And this is going to be the value of E for all of my categories. And here I have my observed values. So what I'm going to do now is I'm going to put all of this information into my TI-83 calculator. All right, so here we go. And what we want to do is we want to put our observed frequencies into a list. So we're going to go to Stat, we're going to go to Edit, and we're going to edit our lists. And in list 1, we're going to put the observed frequencies. So list 1 is going to be all of the O's. So 23, 23, 21, 21, and 19. So I enter those values from the frequency distribution into list 1. In list 2, I'm going to put my expected frequencies, and since they're all equal, I found E to be 21.4, and I put that into my second list, and I put 5 of them because K is equal to 5. There are 5 categories. All right, so now what I'm going to do is I'm going to calculate my chi-squared test statistic. And the chi-squared test statistic is the observed value minus the expected value squared. So I'm going to take that quantity, that difference, and I'm going to square it. I'm going to divide it by the expected value, and I'm going to take all of those and add them all up. Remember, the sigma means to add them all up. And that will be how I calculate my chi-squared test statistic. Okay. So the chi-squared test statistic. Let's go back to our TI. And so what we're going to do now is we're going to go over to list 3, and I'm going to go over to list 3, and I'm going to press up so I can highlight L3. And now I'm going to edit this entire list, and I'm going to say I want list 3 to be equal to, so it's going to tell me what list 3 is right here. If you look here, I'm going to open a parenthesis, and I'm going to let list 3 be list 1, second list 1. So I'm going to take all of these values, and I'm going to subtract from them the values that are in second list 2, oops, forgot to hit the second list 2. So I see L1 minus L2. I'm going to close that parenthesis, and I'm going to square it. So I'm going to raise this to the power of 2 by hitting the x squared button here. So what I have here is list 3 should equal list 1 minus list 2 subtracted first and then squared. And I want to take that and I want to divide that answer by the expected value. Well, the expected values, remember, are in list 2. So I'm going to divide by second L2. So what this is going to do is it's going to calculate all of these individual um, differences squared, and then I'm going to divide all of those by the value, the corresponding value 21.4, the expected value. So let's see, when I press downward, it's going to give me all of those numbers. So these values are all of these, and I'm going to add them all up to get my chi-squared test statistic. So I'm going to second quit. I'm going to quit from there. I'm going to go back to stat, go over to calculate, and I'm going to calculate one variable statistic on list 3. So second list 3. And this will add up all the values in list 3 for me. So I see here that the sum of the values in list 3, the sum of the x's, is 0.523. 0.523. So the chi-squared test statistic is then, the chi-squared test statistic is 0.523. So here I have my test statistic, the chi-squared test statistic, all right? What I want to do is I want to calculate the p-value for this test statistic. And remember, the chi-squared, what we're doing is a right tail test. So to calculate this test statistic, all I have to do is calculate the area to the right of, to calculate this p-value, sorry, all I have to do is calculate the area to the right of this test statistic. So I'm going to calculate the area to the right of the test statistic by going to my calculator. So I bring back out the TI. And the chi-squared is actually under distributions, DISTR above the vars key on your TI. So if you, let's clear this first. And we'll hit second, and we'll go to distributions. And if you scroll down, you'll see the chi-squared CDF. And we're going to use this in much the same way that we were using the normal CDF before. Except we're going to also have to put in the degrees of freedom. So what we're going to do is we're going to, in the chi-squared CDF, let me tell you what the parameters are for that function. The chi-squared CDF, what we're going to do is first we're going to plug in the left, then we're going to plug in the right, and then we're going to plug in the degrees of freedom. So that's for the chi-squared. Let's see here. Let's draw here. We're going to have the chi-squared is skewed to the right. So we're going to have something like this. We're going to find our chi-squared test statistic, which we already found to be, what, 0.523? Yeah, 0.523. But this is with k minus 1, and k is 5. So k minus 1 will be 4. So we're looking for 4 degrees of freedom. So we're looking for the area to the right here. And we're just going to plug in the left endpoint, which is going to be 0.523. The right endpoint is going to be positive infinity, because this continues forever to infinity. And the degrees of freedom are going to be 4, or k minus 1. K was 5, the number of categories. K minus 1 is 4. So let's go ahead and plug that into our TI-83. So we're here in the distributions, and then we're going to go down to the chi-squared CDF number 7. And chi-squared CDF we're going to put in our left endpoint, which is 0.523, 0.523. The right endpoint, which is going to be infinity, or E99. So I hit second, comma, which gives me the E, the exponential notation or scientific notation, E99. And then the last parameter, we have the left and right endpoints, and then we have the degrees of freedom, which are going to be 4 degrees of freedom, close parenthesis, and we press enter, and it gives us our p-value. So we find that our p-value is 0.971. So up here, let's see, the p-value is equal to 0.971. That's a very high p-value. Remember, if the p-value is high, the null can fly. If the p-value is low, the null must go. So in this case, the null hypothesis Remember the null hypothesis up here. We're testing the hypothesis that an observed frequency distribution is equal to some claim frequency distribution. That would be the null hypothesis, that they're equal. Since this p-value is so high, that null hypothesis is probably true. So these clinical trials don't have any, or sorry, I'm thinking of the second example, but these days of the week, uh, these numbers actually do indicate that the um, injuries and illnesses occur with equal frequency on different days of the week. So null hypothesis was that they occur with equal frequency, and we cannot reject that null hypothesis. So most likely, these do occur with equal frequency, and we're basing that on the p-value being so high.